I want to draw a picture of something that you're going to recognize from grade 11, from physics 20. We solved a number of these problems in physics 20 where we had a car. Maybe it's a roller coaster cart, or maybe it's just a car, a go-kart at the top of the hill. Has no speed, no initial speed at least, 0 meters per second. Maybe the hill is, I don't know, maybe it's 50 meters high. It doesn't really matter. It's got a height anyways. That car rolls down the hill. It by gravity rolls down the hill. Got a speed at the bottom of the hill, but we don't know what that speed is. We want to find out what that speed is. You guys remember these questions? Okay, we did a number of these questions in physics 20, whatever class you were in. What did we do to solve this problem? What did we do to find the speed at the bottom of the hill? Yep.
We use the law of conservation of energy.
Good. We used the law of conservation of energy, where we said EI is equal to EF. Maybe you might have said E1 is equal to E2, or maybe you might have said E something is equal to E something else. It doesn't matter. In the end, the total initial energy is equal to the total final energy, right? We're pretty familiar with that. At this point, we would have asked ourselves the question, what kind of energy do we have at the initial side of this, at the top of the hill? Well, we would have said we got potential energy because we got a height. Some people will say we have potential energy because it's not moving. That's not true. We have potential energy not because of the absence of speed, but because of the presence of height. There's a height, therefore there's potential energy. You got anything else on the left side? You got anything else over here or at the top of the hill? Is there kinetic energy up here? No, because it's not moving, right? So we're going to say the left side is just simply mgh, initial. What about the right side? At the end of this problem, at the bottom of this hill, what kind of energy do we have? Yep, kinetic energy, right? Do we have any potential, Justin? Nope, good, just kinetic because there's speed. Now, we don't have kinetic because of the absence of potential or the absence of a height. We have kinetic because of the presence of speed. So we're always looking at what do we have, not what do we not have. Okay, we've got potential because we've got a height. We've got kinetic because we've got a speed. Let me draw another picture now that's going to be a little bit less familiar to you. We got two plates. This is familiar to you. We got a positive charge on one plate. We got a negative charge on the other plate. We got a positive particle right here near the positive plate. This positive particle is at rest, moving at 0 meters per second. We want to find the speed of that positive particle when it reaches the other plate. Now, the distance between the plates, we don't know. That doesn't really matter for what we're trying to do here today. What matters is the potential difference between the plates. The potential difference between the plates, we're going to say is 50 volts. What's going to happen to this charged particle as it's released at the positive plate? It's going to stay where it is. It's going to slow down. It's going to speed up. Is it going to go sideways? What's going to happen to that positive particle? We know it's not going sideways, right? Because we want to find the speed when it reaches this point down here. If we release it at rest, it must be going to speed up then, right? And that's pretty logical, right? You release it near a positive plate, positive particle gets repelled by that positive plate, it's going to speed up. If a charged particle speeds up, how do you think we're going to handle that? Charged particle speeds up in an electric field. We're going to handle that the same way as if a car speeds up in a gravitational field. We're going to say EI is equal to EF. Now, what kind of energy do you think you have at the beginning? What kind of energy do you think you have when the positive charge is at the positive plate? Potential. But it's not MGH potential, right? It's electric potential. Electric potential, if you remember from yesterday, the equation for electric potential is V is equal to E over Q. So the equation for electric potential energy would be Q times V. Instead of putting MGH in there for initial energy, it is potential, but not gravitational potential. So we're going to put in QV initial. What's the final energy? What kind of energy does it have when it reaches the negative plate? Justin? Kinetic energy, because it's moving. These two questions are almost identical. When a charged particle speeds up, It's a conversion of potential to kinetic energy. Just like when the car speeds up, it's a conversion of potential energy to kinetic energy. The only difference here, the type of potential it is. It's not gravitational potential to kinetic, it's electric potential to kinetic. Let's change this question a little bit. Instead of the car at the top of the hill being at rest, the speed of 0 meters per second, let's say this time the car at the top of the hill has a speed of 10 meters per second. How does that change things? How does that change things, Michael? Good. You get kinetic and potential at the beginning of this. So instead of just being mgh initial, it's going to be mgh initial plus 1/2 mvi squared. Equals, on the right-hand side, that doesn't change, right? Because at the bottom of the hill, it's still just kinetic energy. What would happen if this charged particle that was at rest now, for whatever reason, enters this parallel plate apparatus at a certain speed? Let's make it 1,000 meters per second. How would that change? Derek, how would that change? Good. Instead of having just potential QV, we'd have potential and kinetic energy. So once again, it's almost exactly like the first problem, except that we're replacing mgh with QV. Here's another one for you. Maybe this time we don't want to find the speed of the car at the bottom of the hill. Maybe this time we want to find the speed of the car halfway down the hill. The initial speed is still 10 meters per second. The initial height is still 50 meters. What are you going to do on the right-hand side? How are you going to change the right-hand side to match this question now that we want to find the speed halfway down? Do we have kinetic energy halfway down? Sure we do. Do we have more or less kinetic energy than we had when we were trying to find the speed at the bottom? Less, because it hasn't had as much chance to accelerate, right? It's not going to be going as fast. Good. So there is still kinetic energy there. Is there going to be potential energy there? Yeah. Yeah, now it's going to be half kinetic and half potential energy, right? So let's say mgh initial plus 1/2 mv squared equals mgh final plus 1/2 mv squared. What if in this question I wanted to find the speed of the particle halfway across? How would it change the right-hand side? The left-hand part of that equation wouldn't change, right? Initial potential plus initial kinetic equals, well, we'd still have a speed halfway across these parallel plates, but this time we'd have potential energy as well. So we'd say 1/2 mv squared plus qv. Q big V, not little v. Little v is speed, big V is potential. One final question before we flip the page here. What's the initial height here? What's the initial height? Not a trick question. Okay, what's the initial height there? Chelsea? Good. What's the final height there? Still not a trick question, but a little bit harder than the first one. 25 meters. Good. Does that make sense to everybody? We've gone halfway down. The height is half of what it was before. The potential difference is 50 here. Okay? The potential at this plate is 0. That must mean the potential at this plate is 50. If the difference is 50 and the final is 0, then the initial must be 50. So what do we put for the initial potential there? VI. 50. What do we put for the final potential when we've gone halfway across those plates? What do we put for the final potential? Sorry? No. The final potential would be 25. Potential is like height. Maybe we're given the distance across those plates. Okay, that doesn't matter to us in this context. What matters to us is the potential. The potential is like the height. When you've gone halfway down the hill in your car, okay, that's like going halfway across this potential difference. If the height is now 25, then the potential when you're going across that gap is now 25. Does that make sense? Please remember the following. Whenever you're looking at a problem involving a charged particle speeding up, a charged particle accelerating, I want you to think of it as a car going down a hill like this. We can visualize that. We can see that. We can see the color of the car and the number of people inside the car. We can physically, in our minds, picture what's going on. It's much more difficult to picture a charged particle accelerating through a potential difference. But the good news is if you picture the car going down the hill and then just replace MGH with QV, then it's the same thing. So picture the car going down the hill. Do everything like we did on the left-hand side, and then just replace MGH with QV, because it works out to be the same thing. Let's try one more set of diagrams. This one won't be quite as long as the last one. This time, we got our car at the bottom of the hill. This car doesn't have a motor, right? It's a roller coaster, it's a go-kart, or it's something without a motor. So if it's going up a hill, it's going up a hill under inertia, right? Because it had a velocity, whatever. Let's give it an initial velocity of 10 meters per second. It doesn't matter what the height of the hill is. For whatever reason, say the car goes up the hill, we want to find the speed of the car when it reaches the top of the hill. How would we handle that? Not much different than what we just did, right? We'd say EI is equal to EF, but this time at the bottom of the hill, we'd have kinetic energy. No potential, okay? No potential because there's no height at the bottom of the hill. At the top of the hill, well, we'd have potential energy because there's a height, but we'd also have kinetic energy. How would the initial kinetic energy compare to the final kinetic energy? What's more, initial or final in this case? Initial. In the last situation that we had on the last slide, the final would have been more, right? Because we converted before potential to kinetic. Now we're converting kinetic to potential. We lose kinetic, we gain potential. All right. Let's change our setup for our plates. Let's make our plates vertical this time instead of horizontal. Let's make this positive and this negative. Let's make this charge right here a negative particle. Let's say it's given an initial velocity of 10,000 meters per second. However it got that velocity, it's moving at 10,000 meters per second. I want to find the speed of that negative particle when it reaches this plate. Can the negative particle get to that plate? Does the negative particle want to go to that plate? No. Just like this car doesn't want to go up the hill. The only way this car is going to get up the hill is if it's got enough initial speed to essentially have inertia overcome gravity, right? The only way this negative particle is going to get across this gap is if it has enough initial speed to overcome the electric field. It doesn't want to make it across, but it might because it has enough initial inertia. How would we solve this one? Well, the same way. EI is equal to EF. What kind of energy do we have at the beginning of this? Kinetic energy. There's no potential. There's no potential here. This negative particle doesn't want to naturally go to the negative plate, just like the car doesn't naturally want to go to the top of the hill. There's no potential for it to go to the other plate. It does it because it's got an initial speed. What about the final energy? Well, we'd say gets to the other plate. We'd say that what would it have when it gets to the other plate? Yes, it would. Yeah, I'll address that in just a second. That's a good question. I'll come back to that in just a second, okay? Very good question. What kind does it have when it gets to the other plate? Yep. It's got potential energy. Why? Justin just asked the question. Wouldn't it want to go back to the other plate? Just like the car wants to roll back down the hill, maybe it does, maybe it doesn't, but it wants to roll back down the hill. Okay. This charge will want to go back to the other plate. Yeah, it's got potential to go back to the other plate like this car has potential to go down the hill. So, yeah, I don't know. Maybe it does go back to the other one. Okay, maybe it doesn't. Depends upon how fast it's moving when it reaches the other side. But it definitely wants to, yeah. We do have potential when it reaches the other side, just like we had potential over here. What else we got? Well, assuming it's still moving when it reaches this plate, didn't just barely make it, we're going to say it has kinetic energy as well. How's this different than the problem on the left? Instead of having MGH, we got QV. right? On the last slide I had up, I said, whenever you have a problem with a charged particle is speeding up, I want you to think of it as the car going down the hill. Potential to kinetic energy. Now I want you to think when the charged particle is slowing down, I want you to think of it as the car going up the hill. You know how to solve this problem and this problem. So there's really no reason out there why you can't solve this problem and this problem. Because they're the same, except that we sub in QV whenever we have MGH. All right? Let's do a problem here, guys. Page 571. Pith ball of mass 2.4 times 10 to the negative 4 kilograms of the positive charge. Pith ball. What's a pith ball? Listen, we're reading questions, and sometimes we see a word. We don't know what the word means. Sometimes it matters. Sometimes it really matters what the word means. Sometimes it doesn't. In this case, it doesn't really matter. You can get past the whole pith ball and just answer the question based on the physics of the question. In the end, if you're curious, a pith ball is a tiny little ball, really, really light ball. You can see 10 to the minus 4 kilograms. It's made from the interior of a plant. Pith is an interior of a plant. And it works really well with electrostatics because it is so light. Okay, it's so light that the electric force doesn't have to be incredibly strong because we've got such light objects. We notice the effect. We can notice forces on these little light pith balls. Anyways, this pith ball has a charge of 1.2 times 10 to the negative 8 coulombs, and it's initially at rest at location A, which they've nicely drawn a diagram for us. Right down here at location A, we're saying it's at rest. You know what? Not a bad idea to write in 0 meters per second down here. It doesn't say that on the diagram, but we know that it's at rest, so let's write down 0 meters per second VI. At this location, it has this much potential energy, electric potential energy. So I'm going to say this is EP initial. When it's released, the ball accelerates toward the larger charge. Why does it accelerate toward the larger charge? Because it's positive and the larger charge is negative and it's attracted to it. Position B, the ball has 1.5 times 10 to the negative 8 joules of potential energy. Why does it have less potential energy? Tell me why it has less potential energy here. Because it's speeding up, right? And if it's speeding up, it gains kinetic energy and it must lose potential energy, right? Step back from this question for a second. The big picture of this question. What do we really have here? What's really going on? Not anything crazy, complicated math, no equations, okay, no complicated physics principles. What do we really have going on here? A charged particle is doing what? Charged particle is speeding up. What do we do when a charged particle speeds up? We picture a car going down a hill. Simple as that. When a car goes down the hill, we always use EI is equal to EF. What kind of energy does the car have if it starts at rest at the top of the hill? It's got potential. Right? The car would have MGH, right? We'd replace that with QV because we're dealing with the electric potential here instead of gravitational potential. There is no kinetic energy because it's not moving at the top of the hill. Picture this car, right? Picture this car. Bryce, you got this car pictured? Yes? Really? Do you really have it pictured? What color car is it, Bryce? Red? Is it like a deep red? No? Okay. How many people in the car? Just one person, boy or girl? Old or young? Are you just making this up or do you really have this pictured? You really have it pictured? Okay. What kind of car is it? Oh. Old or new? Old, like what year about? Any rust on it? Yeah, okay. Good. Picture the car going down the hill. That's much better than most people in the past have done, by the way, Bryce. So the car is going down the hill. We're picturing it, right? It's at rest. We know when it's at rest, it doesn't have kinetic energy. We know it's at the top of the hill. We know it has potential energy. Okay, that's exactly what we've written down here, except that it's QV instead of MGH. Bryce, when that car gets, wait a second, have we made it all the way down the hill? No, we haven't. We made it halfway down the hill. I don't know about halfway, but we made it partway down the hill, right? What kind of energy does this Jeep Grand Cherokee with some rust, with one person in it, one young person in it, what kind of energy does it have when it's gone part way down the hill? Okay, you're still picturing this, right? It's going down the hill. What kind of energy does it have as it's part way down? Victoria, what kind does it have?
Sorry.
What kind does it have? Yeah, it's got potential and kinetic energy. So we're going to say MGH final plus 1/2 MV squared. Final. But we're going to replace MGH with QVF, right? Good? We get a bit of good news here, actually. We know the value of QVI already. We don't need to multiply those two numbers together. We know its value already is 3 times 10 to the negative 7. If we didn't, that's okay. We multiply Q times VI. But when we have the value of the initial potential energy, just fill it in. The final potential energy, oh, it's 1.5 times 10 to the negative 8. Plus 1/2 of the mass, 2.4 times 10 to the negative 4, times VF squared. Let's do this on our calculator to make sure that we can do it here. 3 times 10 to the minus 7. Let's subtract from that 1.5 times 10 to the minus 8. Let's multiply that by 2 to get rid of the half. And let's divide that by 2.4 to get rid of the 2.4. And then what do we got to do with that now? We're almost there. Nathan, what do we got to do with that? Right. Let's square root that. We end up getting 0.0487, or we're going to say VF is 4.9 times 10 to the minus 2 meters per second. Okay, if this is an old, rusted, red Jeep Grand Cherokee with a young man inside rolling down a hill, okay, we're going to nail this question, right? If this is a situation where a pith ball that has a certain charge is accelerating, we seem to get bothered by that. Something seems to not click with us as easily as it does when it's the Jeep Grand Cherokee going down the hill. So picture as the Jeep Grand Cherokee going down the hill, and then just replace gravitational potential energy with electric potential energy. Got it? All right, going to work on these two questions for the remainder of class. If you don't finish them, please finish them up for homework tonight.